before, after study, during the day. A mask is required, and again, this is a requirement by CDC to help us mitigate the spread of COVID-19. We appreciate that. Just please be sure you're wearing a visible ID. This helps us to be sure that we have control on who's here on campus, and for your safety, we appreciate that. School safety, again, is one of our top priorities in our high school. So if you have any questions, please see one of the officers or you can see one of our administrators in the hallway. We'll be glad to assist you. We're glad you're here this morning. We hope all of you have a great day here at AHS.
Okay, so yesterday we talked about Precambrian, and it was a very long period of time, but I could fit it all into one lesson because basically it was bacteria. There's not too much. I mean, we talked about the word stromatolite, and it's sort of the upward growth of the, whether it be algae or cyanobacteria. But we're getting into the things that may have exoskeletons, but they do not have internal skeletons. That will be tomorrow when we get into more of the more advanced organisms as time goes on, as evolution was occurring. So when did trilobites have their heyday? When is their index period for? Right. I mean, you come in here with food. Yes, you need to hurry that. So, both of you do.
What?
No, and you shouldn't be eating in here either. But you both need a. Oh my God!
Hey, you look
so
very
frustrating.
I did not understand it. I did the same thing. I just got food.
So, when did trilobites dominate the seas? It was in the Cambrian, yes. Now they lasted. The Cambrian is a very, very narrow window, but that is when they just exploded, like they were everywhere. Yes. Okay. Okay, I'll get to it when I can. Okay, good. Well, please, fingers crossed. Yes. All right. So why was the trilobite so important in the fossil record? And I think I actually already said the answer. I didn't realize that I was answering the second half. Why were trilobites so important? Yeah, and they were for a very distinct period of time. Now there are different types of trilobites, okay? And some of them were more prevalent, I guess is the right word, in certain time periods than others. But there, we will be talking about specific index fossils in specific time periods. The trilobite is not the only index fossil. You're doing invertebrate or non-vertebrate. They had exoskeletons, or at least a portion of them, had some type of chitin. Even your plants, they developed protection from the sun as they started moving shallower. Otherwise, they all basically got fried by UV rays. So the exoskeleton is a direct adaptation to the motion from deeper in the seas, where the water protected them because they were far enough down. Actual ocean water absorbed the harmful rays of the sun, to moving more towards the coast, where they had more exposure to the sun. If they didn't develop this, I didn't bring a paper out for me, I don't think. Yes, it is. If they didn't develop this adaptation, then they wouldn't have made it. This time period, the entire Paleozoic, started about, it's not like an exactly on this date, no. About 570 million years ago, which is what MYA stands for, to about the time that Pangea actually formed. There are a couple of different dates that I see as far as the Permian extinction, which is what we're going to be talking about Friday. But we had a nice, let's see if I can do my math. We've got 325, if I just did that right in my head, 335? No, 25 million years worth of time where we had a huge change in diversity of the flora, and so the plant life, flora, and then the fauna, which is the animal life. Not quite moved on land yet. We're getting ready to. I mentioned yesterday a few times, it's the ice ages that allowed for protection from the sun, promotion from deeper to shallower, gave these animals the time that was necessary to do these adaptations, to evolve. And if it wasn't for the various ice ages that have punctuated Earth's history, these processes of evolution would take, at least for these organisms, would have taken a much longer time to adapt to the change in the environment. Snowball Earth happened over a long period of time. The Earth itself was not completely frozen with its water. There was still like some slushy areas towards the equator. The one before this, the one that was 2.5 billion years ago, that allowed photosynthesis to occur, we are pretty sure that the Earth was completely frozen as far as the liquid water through the entire planet. As we go through glaciations closer to the present, your glaciations themselves are shorter, which means it's not as much time in order for the planet to freeze. And as we go closer to the present, yeah, you've got glacial motion, but it's not all the way from the poles to the center. Why would you look like that?
Because you're not in the system.
Oh, really?
Yeah.
That's weird. The Sturtian is the furthest back. These were able to get my appendix book out. Oh, we're gonna put my appendix book. Here. I'll go forward. Something else. Oh, the Marinoan would be next. You have longer time periods with those. The gas gears is actually the shortest of them all. The last two, these are what triggered the explosion of life. We call it, and I don't mean like they literally blew up. It's just we had such a change in biodiversity of both plant and animal. These two immediately preceded the Cambrian. So the ones that are in red, those are the two that really allowed these organisms to mutate. And mutation is not a bad word. It allows them to adapt to their environment over a shorter period of time. And compared to the two that are not in red, they're very, very, very short. You are literally ending the Precambrian with this one, and you are literally starting the Cambrian with the last one. But all of these together are what we affectionately call Snowball Earth, or the Cryogenian Ice Age. So, like I said, the first one that we really have record of, the Carolean, that was 2.5 billion years ago. That was the one that allowed for the adaptation of photosynthesis. We had another, these were more for advancing multicellularity, but the ones that are in red, that was the ones that allowed for exoskeletons. We didn't have really internal skeletons yet. Now, we had a bunch of different time periods in the Paleozoic. It starts with the Cambrian. We were in an ice age at this time. I went back and I took a look at the oxygen record. And you either are starting an ice age or you are ending an ice age. And that's sort of what truncates the different periods of the Paleozoic. Cambrian was first, that's the furthest back in time. Ordovician, we had a massive extinction at the end of the Ordovician going into the Silurian, and then we had another massive one at the end of the Devonian going into the Carboniferous. The Carboniferous is when we had a huge, and there's two different periods that are in there. There's the Pennsylvanian and the Mississippian. That is when we had a huge amount of plant life that invaded the land. And I don't mean invade like that way, but it made its way much further inland. The Silurian is where that started. But we didn't get that really cool vasculature and those seeds until the Carboniferous. And the reason why they developed here was because the other thing that showed up in the Silurian were insects. And the insects that were preying on the spores for the plants, they're taking away their babies. And so they had a genetic adaptation that we call a seed coat. And it protected them from not only insects, but also from desiccation, which just means drying out. Because before we had the seed coat, and before we had an internal vasculature, the xylem and the phloem, the plants were literally stuck around their water source. They couldn't go far into the land. The first pretty crawly things that came out of the water, the things like snails, gastropods. The first things that took to the sky and really colonized the land, those were insects. And those dragonflies were huge. We're not going to do plant and insect invasion until Thursday. So today's the non-vertebrates, tomorrow's the vertebrates, and we'll do plants and insects, and then we'll have the Permian Triassic extinction. After the Carboniferous, we started having Pangea slamming together. And what happened when the ancient continents came together to make the supercontinent, most life was trying to thrive around the water. As the plates came together, they collided, they lifted, there went your water source. And it got really hot, really dry. And that wiped out 96% of all life on the planet at the time. Well, at least marine. Land organisms were a little bit better off than our marine life. And then we had a million-year-long volcanic eruption in Siberia. And we will talk about that more on Friday when we do talk about the mass extinction that ended at the tail end of the Permian, going into the Triassic. So, big things, and there's a couple slides that actually answer this part on the notes. Oh, that A is not, I'll fix it. Development of skeletons. And when I say skeletons, it's primary exoskeletons. I don't know why my OCD is like being bothered so much by that, but that is not blue. And it's bothering me. Let me bring that back. And I need to double check my attendance again. But we had development of exoskeletons, and it was everywhere. And it was not, there's Jimmy. It was not just the animals, but it was the plants too. There's Mauricio, there's Sarah. Okay, Colton, Erica, Jimmy, Joseph, Mauricio, Sarah, Taylor, Chase, Braylon. All right, I will check one more time. Go back to the right slide. And like I said, the exoskeletons was a direct mutation to protect from the ultraviolet radiation from the sun, the stuff that gives us skin cancer, causes sunburn. Organisms, before they had these shells, these protective chitinous skeletons, most of your marine life consistency was very similar to like a sea anemone, like very soft, very delicate. And it does not take much UV radiation to negatively mutate an animal. So skin cancer, sunburn. We've been out in the sun for too long without any kind of protection. You know that it's nasty. I mean, it's necessary for life because you know it, but it's still a hydrogen bomb. Predators were all over the place. And like I said, we have this nice gradual motion from much deeper in the ocean towards the shoals, towards the shallow area. Shelly fauna. Okay, but fauna, you've got flora, and you've got fauna. Flora or plants and fauna are animals. Now the plants started developing these things too. I just realized I had that basically on the same thing on the two different slides back to back. You already talked about the protection from the UV radiation to allow them to go closer to shore. The fancy word for drying out is called desiccation. Now, I mean, we've all seen when it rains, the worms come out because they don't want to drown, because yes, worms can drown. Yes, they sure can. That's why they come out of the ground. They don't want to drown. I mean, not that they're like thinking, I think, consciously about that, but yeah, they don't want to drown. So they come out and you can see them sort of crawling around on the sidewalk. But sometimes they don't make it back out. And they literally dry up and they shrivel up on the concrete. Okay, that's called desiccation. These shells, these exoskeletons, help keep the moisture inside the organism, whether it be plant or animal. And it protects it from predators. And it gives it that extra protection from the radiation. So there's multiple, and it also helps give them support and structure, especially in the case of these plants, these sessile filter feeders, which just sessile means it doesn't move. It's anchored, it's tethered. A bunch of scientific terms for everything today. These are various types of shelled organisms. I showed you an image like this yesterday when we were sort of ending up. You don't necessarily need to know these guys' names, but we see a lot of this spiral shape that's about to happen with things like the ammonoids and the gastropods. Sometimes they're spiral instead of just circular, like spiral going up, pointed. Some of them look more like clam shells and oyster shells. And we'll talk about some of them in particular. I'm going to have a slide specifically devoted to trilobites. I believe it's the next one. Trilobites. Benthic means ocean floor. That's what benthic means, or bethanoic is the other way that I've seen it. Mobile means the trilobites could crawl around, and some of them actually swam. They were completely mobile. They were some filter feeders, which is more often than not early in the Cambrian. Some of them were more predatory. Brachiopods, they sort of look like clams, but the way that their valve is. What? No, Siri, stop. I don't even know what I said to make you talk. Go away. I don't have a body, so I probably look invisible. What the heck did I say that made, oh gosh. I swear this phone, I'm just not used to it. Don't.
Hey, Siri.
Did I say sessile? No, don't listen to him. No, don't. Brachiopods do look like a clam. It's not a bivalve. When I show you the picture of them side by side, you see what I mean. Its midline is different than an oyster or clam. This last one, this is essentially a sponge. Archaeosapid. It is literally a sponge. These were the first things that helped build reefs, which are extremely important. That's where a lot of ocean life likes to hang out, is around their dead bodies. We have all different kinds of pictures to show you. All right, trilobites. Had to have the ice age in order for these guys to really develop that nice hard exoskeleton. They are an arthropod. They're very similar to a miniature horseshoe crab. Now, I say that. Some trilobites, well, they were like 2.5, 3 feet. Like they were very, very, very large, but most of them were not. They were small. Some of them were sediment filter feeders. Some of them were predatory. We're not going to go into the individual species of trilobites, but they were not all exactly the same thing. Because there are all different shapes and sizes of them. Some of them are itty bitty, like the size of an eraser pen. Some of them fed on plankton, therefore they're predatory. Plankton has been around forever, or at least their ancestors. The things that look like itty bitty, teeny tiny little shrimp. The trilobites that could swim and the trilobites that were predators, those were the ones that survived the miniature extinctions that kept occurring. We've had 5 major extinctions, the big bad ones that wipe out the bulk of life, whether it be plant or animal, but we've had lots of smaller extinctions. Oh, yeah. It's the average life expectancy of a species is approximately 3 million years. Give or take.
How long?
Around 2. If you go way back to the hominids, like the beginning of our evolutionary line, yeah, it's been about 2 million years. So it is kind of scary. And I said that's the average. I mean, you get a big enough asteroid slamming into the planet, we have another Cretaceous extinction.
This is why we go to the moon.
This is why we need to go to the moon. There is no viable atmosphere for us on the moon.
Oh. I'm sure.
What anoxia means is there are various climate changes that can occur that reduce the amount of oxygen that is available in the ocean for these things to breathe. It is anoxic. It is a toxic depletion of oxygen is what that word means. The ones that could swim and could get further off the bottom of the ocean where it was more shallow, there was more oxygen, and those were the ones that were adapted to be able to propagate future species. These are trilobites. These are trilobites. Some of them were this large, like literally bigger than this, but which you can see on the projector. Tri meaning 3, lobite meaning lobe. It's literally what trilobite translates into. It has 1, 2, 3 different sections to it. Is why that is called a trilobite. I didn't just pull a name out of nowhere. Very, very similar to a horseshoe crab. If you flip it over, you can see all the little eggs on the underneath, and then they have little peachy things in the front. Very, very, very old body style for a horseshoe crab. Brachiopods next. I cannot tell you how many times the brachiopod has gone to the brink of extinction, but then exploded again on the back end of it. Brachiopods are all over the fossil record. Different species of brachiopods at very specific times, just like trilobites. It wasn't until a couple of very specific extinctions that the trilobite completely went away, but the brachiopod did not. The one on the left is a brachiopod. The one on the right is a normal bivalve clamshell. This midline, well, they can't see what I'm pointing at. Our modern day clams, their valve is on that axis. Where in a brachiopod, instead of it opening on the axis where it's symmetrical, it's one of the bottom part of a brachiopod has like a bigger cup than the top part. Almost looks like a messed up Pac-Man kind of thing. But a regular clamshell, a normal clamshell, they're symmetrical on both sides. Very, very, very closely related. It's if you've never shucked an oyster or opened a clam, there's like a tendon kind of thing that holds it together. That is where its valve is. I mean, some of you know exactly what I'm talking about, and some of you have no idea what I'm talking about, the internal part of the clam. Sponges. Okay, this is the Archaeocyathid. These were the beginnings of reefs. Now, we had corals after this, but these sponges were the very, very, very first reef builders. Extremely crucial to providing a habitat for other organisms that end up living in their dead bodies, which is like messed up, but that's the way a reef system works. Part of the reef are the ancestors that were dead. It provides the bedrock for the other living organisms to then make their home. It's how they work. Now, sometimes entire reefs die. We've polluted the snot out of the ocean. Once a reef is totally dead, it's almost impossible to bring it back. But the foundation for a healthy reef is the ancestors' dead bodies. It's fish. We'll talk about the vertebrates and the fish tomorrow. It's very, very, very early stages. This particular, now the one on the left is not a fish. That's a different kind of predator that's actually related to a brine shrimp. But the one on the right, some fish have bones, okay, and some fish don't. And they have cartilage. Cartilage does not fossilize. Bone fossilizes. Your first fish, if anything, its teeth, just like sharks. The shark's tooth is the most common fossil period that you can find because they're constantly regenerating them. And there's so many dang many of them. Fish have changed drastically from the beginning. The rays and the sharks, with the exception of getting smaller, really haven't changed that much at all. They predate the dinosaurs by a very long time, and they're going to be around for a long time to come.
How long is
When did sharks develop?
how long has it been around?
I have to cheat and look at my timeline because I don't remember all the years. I'm not a walking encyclopedia.
Well, I'm stuck on that 2 million year thing.
No, I know, but I have to look because I could have sworn. Okay, so of course it's so small I can't read it. Ravens and shark. Well, it was in a Devonian, but that would have been approximately 420 million years ago, give or take.
So,
A long time ago. Whereas the first dinosaurs, the true dinosaurs, they didn't show up for almost 200 million years after that. The shark body structure is almost perfect. It really is. It just hasn't changed. This Animalcaris, this is like a gigantic brine shrimp, and it was a nasty predator too. Gastropods. There's two major structures that you see. One is what you think of as a normal spiral snail shell. The other one is sort of like a pointed one. The shells look really similar to snail shells, but the organisms that live, both the cephalopods and the gastropods, they're actually closely related to a squid. The ones that I'm showing you, most of these are awesome index fossils. The Ordovician, cephalopods were everywhere. That is the most prominent index fossil from that particular time period. You had bryozoans, which almost look like a, I don't know how to explain it. Not quite like a golf ball, because it was more square in shape, but it was a very, very specific plant that happened in this particular time period. Corals started. You don't necessarily need to know the difference between tabulate and rugose coral, but this was the beginning of the huge reefs. The sponges started at first, then we had corals develop. Lots and lots and lots of suspension or filter feeders. So that just means that those organisms couldn't move. Like, yeah, they could sort of like sway in the water, but they couldn't get up and walk. They were tethered down, essentially by roots. We just didn't have the development of true roots yet. That came much later, much later, the plant life going on there. And at the end of the Ordovician, there was another ice age problem. I say problem. It caused the extinction of the major organisms at the time, but it allowed others to flourish and become now the apex, not necessarily predator, but the apex organisms. Glaciers formed, froze water, sea level goes down. It's all marine life at this point. It gets desiccated, exposed to sunlight. If it doesn't have any kind of protection, those all died out. And there was a huge extinction event. Cephalopods. They were another index fossil of the Ordovician. There are two major types of cephalopods. The one on the right, the ammonoids, those are the ones that ended up going extinct with the mass extinctions. These have this ridge that's sort of like a backbone kind of thing. And yeah, the other guys do too, but it's not V-shaped. They're both spiral shaped. The ammonoids went extinct. The cephalopod on the left, the nautiloids, they did not go extinct. Same spiral structure, just there's a different ridge on an ammonoid that's not present on a nautiloid. Silurian and Devonian. All right, more ice ages, huge reefs. all different kinds of varied life. It's the coral specifically that just huge, massive, monstrous reef systems. Sea scorpions are extremely prevalent here. That's an index fossil for the Silurian. In the Silurian, towards the end was the beginning of things moving on land, both plant and animal, specifically insect. Ammonoids are still present with the Silurian. The period after the Silurian was called the Devonian, and that was another mass extinction. And we have hundreds of millions of years between some of these periods. I'm gonna dig it up. The glaciation at the end of the Devonian was more severe than the Ordovician. Once again, froze the water, sea level went down, wiped out all the reefs. The reefs that came back after this time period were patch reefs. In the Devonian, they were huge reef systems, huge coral reefs. I need to. Oh, I put a picture of a sea scorpion on here. Obviously, this is a 3D rendition. I didn't put the actual image of a fossil, but it flattened that guy out, and it almost looks like it's got like whale fins sticking off the side. It's not, didn't have a stinger like modern day scorpions or anything like that, but these were apex predators at the time. Carboniferous had two parts. The Mississippian was first, and then the Pennsylvanian was second. Crucial to the formation of coal, huge index of plant or influx of plants going not just on to the land, but going deeper inland. We will talk more about the plant adaptations on Thursday. But most of our coal comes from all of these plants. We started seeing amphibians and reptiles evolving and moving on to land at this point. I'm getting ahead of myself. We're getting vertebrates tomorrow. You have the bryozoans and the crinoids. I don't know if I put a picture of those on here. I don't think I did on this one. I think it's on the next one. Huge influx of these sessile, these stuck filter feeders. The huge reefs of the Devonian, they completely and totally collapsed. They all died, but we started to have other reefs coming back in small sections or patches. That particular, I'm pretty sure I have one of those in this box. That index fossil. I took this home over the break, hoping that they had like a lab in here. Devonian, Mississippian. Nope. Okay, this is. One emperor, here we go, 26. 54, 25. I need to take this back home and go through it. Now that we're actually getting into the fossil record, we're not just talking about periods of time. There it is. They almost look like seeds, but they were shellies. They were living organisms. Crinoids should be on here. Yes, I do have the fossilized version of this as well. More similar to what you think of as an anemone. Believe it or not, we're related to that thing. We're a primal, what we call a notochord. No, it did not have a brainstem like what we think of, but we share a common ancestor, a deuterosome with these. So yeah, we're related to starfish and sand dollars. Very distantly related to them, but we are. It has to do with the fact that you're starting to create the pathway for controllable nerve endings. I'm pretty sure that these, it would have been touch sensitive, so it wasn't like reaching out to grab things on purpose. It was more of a reflex like jellyfish. But yeah, we're related to these odd things. These were filter feeders. They were passive feeders, filter things like plankton and other specific compounds out of the water. They did have that calcium carbonate, which is how you read that, exoskeleton, and that's the part that's fossilized. Without that chitinous exoskeleton, there's just not much for us to be able to see. That's the last one for today. I got through that a lot faster than I expected because there were so many different organisms. This is why I could not do all of the Paleozoic in one period. There are just too many organisms that I do need to talk about. Let me stop this.